All right, so thank you everyone for finding time to join this session. I am Naftali Kimani from Kenya. I'll be chairing the session. And at the interest of time, I think I'll invite our first speaker, and that is Ayodeji Ibitoye from the University of KwaZulu-Natal, Republic of South Africa. He will be sharing with us some work done on cosmological parameter estimation with thermal Sayesov-Zeldovich effect and projected density field. Ibitoye, the floor is yours, please.
Thank you for having me. My name is Ayodeji Ibitoye, and from the University of KwaZulu-Natal, working with Professor Yinzima. I'd like to thank African Astronomical Society for putting such a meeting like this together. Please, can you confirm that you can hear me very well, sir?
Yes, we can hear you.
Okay, thank you. Thank you for giving me this privilege to talk on this so that we can have other scientists to look at what we're doing and share their views, make comments, constructive comment that can help us to move forward and get better. So I'll be talking on cosmological parameter estimation with Zeldovich effect and density field. And the aim of this work actually is to constrain the Planck-Tamarhezy effect mass bias parameter and the linear clustering bias BG for galaxies and WISE, and I'll explain how we arrived at our constraints. So the flow and presentation I will need to talk about the motivation for this project, what data we're interested in, then how we measured and modeled the auto and cross-path spectra, constraint that we reached, and conclusion. Bolit et al. 2019 confirms again what Planck 2013 excess paper said, which is that there is a tension that exists between the estimation of cosmological parameters between CMB-based and cluster-based experiments. Well, we know that the estimation of sigma 8 and omega matter depends on, the estimation of these parameters depend on the so-called hydrostatic mass bias parameter, which is a parameter that quantifies the uncertainty in the cluster mass estimation in the Planck analysis. Or one can say it's the parameter that tells us the deviation of Planck estimated mass, cluster estimated mass from the true mass of the cluster. And so since this parameter the estimation of this parameter depends on the mass bias, then it might be a good thing to look at to study the hydrostatic mass bias parameter. And Bolit also infers that about a higher value of the mass bias parameter is needed to reconcile these tensions, and we would see if we're able to achieve that in this study. So we use two data in this project. One is the Compton parameter map and the data from wide field infrared survey explorer data. Starting with the Compton parameter map, the inverse Compton scattering of CMB photons by ultra-ionized gas around galaxy clusters are captured by the Planck satellite and in some way builds up into a map. They use some algorithm to suppress the galactic and extragalactic foreground while they enhance the signal. However, there are still some residual foreground in this map, which eventually we would need to account for also in our theoretical modeling. Planck also make available the galactic marks with which we can mark the galactic region and in a way further suppress the contamination from galactic region. One most important thing about TSZ is that it's independent of redshift, so it's a good tracer with other observables, as it were. And yes, so yes, the Planck TSZ is actually delivered in an answer of 2048, but for the analysis we're interested in, we degraded the resolution to answer 512 because 512 will be sufficient for such an analysis that we're interested in. The second data is from the wide field infrared survey explorer. The WISE satellite actually scanned the whole sky in 4 photometric band W1 to W4, and the catalog contains positional photometric data for more than 500 million sources, but which includes the satellite scan, galaxy, stars, etc. But we're only interested in the galaxy. So following the criteria outlined in Ferraro 2015, we're able to extract the galaxies from the query the galaxies from the catalog and project them onto an ePix map. And when we build the map, this is how it shows that you see. Again, the foreground, the galactic plane will be marked also by the Compton parameter marks, which we actually did in as well. To ensure 95 completeness of WISE, we made a cut of W1 less than 16.6 magnitude, also reference from Ferrari 2015. We know that WISE data, photometric data, cannot yield direct estimate of objects, meaning that we need the redshift distribution of sources. And so we adopted a statistical distribution of galaxies derived in Yan et al. 2013 via cross-matching with SDR7 data. And for the sake of a theoretical model, what we did was to fit the histogram. We modeled the redshift distribution analytically to allow us evaluate the expected galaxy number density for any value of redshift within the coverage range, as this will also be needed in the theory to match data. So this is just what I put up to convince myself that this is the direction of flow for this project. The theory and data, the theoretical prediction, measuring power spectrum from the data, so that eventually I can sort of compare apple with apple. Also from the data, we were able to compute the covariance matrix. I need to point that we used PostSpice, a software called the Spatially Inhomogeneous Correlation Estimator for Temperature and Polarization, which allows us to, for any given full sky map and its corresponding mask, you can output the power spectrum and its corresponding covariance matrix. And so given the individual marks and also the joint marks together to PostSpice and corresponding marks, we are able to output the power spectrum, which I'm going to show us, and the covariance matrix for each of these observable. So for what we measure from WISE, we call it GG, from TSZ, Planck TSZ data, we call it YY, and the cross is GY. And from these, and the essence why we do this is to be able to maximize the statistical information we have in our measurement. PostSpice can only provide a covariance matrix for each of these observable, but cannot give us the half diagonal terms, which is a cross covariance between different measured spectra. And so how did we obtain this? We obtained this from using the individual covariance of this measured observable to generate a realization. And then from there, we converted that, we take that into ALM space, from ALM space to map space, marks each of the realized maps, and we're able to output the spectras, the realizations of the spectras, from which, going through the methodology, we obtain the cross covariance between measured spectra. And then going from there, using the covariance, using the formula here, we're able to output the cross correlation coefficient, which tells us that the diagonal for the, well, maybe it would be good to call it autocovariance, are normalized to 1 as expected. And now to the Planck Tama LZ angular power spectrum. What did we get from this data? So the black dots is the measured power spectrum, and the uncertainties, the error bars, are calculated from the square root of the diagonal of the covariance matrix. We measured the significance of 48.2 sigma on this, and we modeled the ELO contribution into the TSZ from 1 ELO and 2 ELO. The 2 ELO term actually gives us, it accounts for the correlation between ELOs, while the 1 ELO term is contribution from an ELO. We call it intra-ELO contribution. And we also take into account the residual foregrounds in the Compton parameter map by summing up what we get from the theory of the TSZ with the foregrounds. And these are the spectrum these are the spectras, the foreground spectras, the CIB, radio point source, and instrumental correlated noise, weighted by their individual amplitude. The template for these foreground spectra were taken from Bolit et al. 2018, and Makia also used the same to Makia et al. 2018, and since it's available in literature, we adopted that in this work. And having added that hop, so the summation of all of these foreground spectra will give you the purple dot. And when we sum that to the TSZ, we're able to recover the observed spectra smoothly. On the projected density field power spectrum, again, we measure the spectrum from post-spice, which is the points, and the error bars again are from the covariance output from post-spice. The blue is the 1 elotam, the modeling from elo model, and the orange is second elotam. The green is the total elo. One thing I need to point out here straight is that because of the discrete nature of the WISE galaxy catalog, and it's splitting into different pixels, it's possible that a short noise component is induced in the overdensity map that we constructed. We reconstruct from WISE data, and this can bias the computation of this spectrum. And so we had to deal with this by following Makia et al. 2018 and Ando et al. 2018, where we got the idea of splitting the catalog into two, and from this way you can compute the half sum and half difference and have the short noise extracted out. The short noise is where it's not really categorized the foreground, but in a way, it's something that comes to account in the discretization of data because of the way we querying the catalog to reconstruct the map. So we need to take that into account. Then we model this observed galaxy power spectrum using an elo model that parameterized parameterized by the linear galaxy bias, which is weighted by the first elotam and the second elotam. But it is good to allow such a galaxy bias to evolve in redshift, which we did in terms of its amplitude at z equals 0 and on the power law alpha. So this way we are sure that we are taking into account, we are evaluating the BG across redshift that's contributing to this spectrum. And the dictation is about 23.6 sigma. But it appears as though the 1 elotam is, the theory is largely driven by 1 elotam. Well, I would like to say one or two things about that, comment on that as I progress in this presentation. Then it will be convenient to talk about the cross correlation here. Yes, I just need to also permit me to remind or point out that the theoretical power spectrum, shown here and here are not the theoretical power spectrum computed straight from theory, as it were, from calculation, but they are theory that has been we've taken into account the modeling of the observational effect. So we included the effect of the beam convolution or the artificial mode coupling induced by the max. We used the recipe provided in Yvonne et al. 2002 to be able to do this. So that way we're able to compute the resulting pseudo power spectrum, which takes into account the observational effect, and then we match that with the data. Yes, this correlation is to about 9.6 sigma, which is something good. And this plot to the bottom is actually the cross correlation of WISE with the frequency, the Planck CIB frequency map. So why did we do this? From Makia et al. 2018, it suggested that for TSZ cross correlation that has to do with galaxy data set, there is a possibility that there is a contamination from the BCIB coming at redshift equals to 1 and above. And because WISE satellite probe galaxy up to redshift of 1, we decide to take into account this, and we evaluated or estimated the effect of the CIB contamination in the cross correlation by cross-correlating the WISE map with each of the Planck CIB frequency maps, and we realized that they are actually similar. They show a similar multiple dependence. So what we just did was to take the average, which is, oh, sorry for the nomenclature. The average is the orange, I think. Yes, the orange. And so we weight that is weighted with the parameter we label BCIB, and we can see that indeed in the cross correlation, it contributes at the high heads, which help us to recover the observed measured spectra eventually. And to our results, this is a table showing our work in comparison with previous data, with previous work done on constraining the hydrostatic mass bias parameter. And we find out that the value we got is broadly inconsistent with literature. The Makia that I spoke about is actually the last part on this part. We divided into two to show the TSZ-based experiment and the weak lysine experiment. And it's broadly in agreement with the literature. And so here we discuss our results.
You have 1 minute, please.
Okay, here we discuss our results, which is the constraint of the 7-parameter space, the foreground amplitude, the BCIB that we introduced to quantify CIB contamination in the cross-path spectrum, the BJ linear clustering galaxy bias, and the B. So what does this tell us? This result looks to be the tightest to date. However, what inhibits us from drawing serious conclusion is because the spectrum seems to be likely driven by the 1 elo term. Possibly, maybe another model like the HOD model would be good to justify this. But the value we reached on B seems to be very good and consistent with literature. And this actually, we can conclude that the constraint reached for our parameters, they are effective to recover the observed path spectra. And our estimate on B, actually, which is the major aim of this project, actually suggests a 40% decrement of the TSZ mass with respect to the true cluster mass. This might help to recover the tension between CIB-based and cluster-based experiment. We also suggest that for such a TSZ cross-correlation study, it might be important to consider the contribution from CIB. Thank you.
All right. Thank you very much, Ibitoye, for the exciting discussion on the estimation of cosmological parameters. I don't see any question, but for the interest of time, I think we will go to the next speaker. And if somebody has a question, then the discussion can continue on Slack. Thank you so much, Ibitoye. So our next speaker will be, you're welcome. So the next speaker will be Imogen Whiteham from the University of Oxford in UK, and also in collaboration with the University of Western Cape in South Africa. She will be giving a talk on exploring radio galaxies with a MIGHTY survey. Whiteham, the floor is yours.
Okay, great. Hi. Hopefully you can see my screen okay?
Yes, I can.
Okay, brilliant. Thanks for the introduction. So I'm Imogen Whiteham, and as you said, I'm going to talk to you today about exploring radio galaxies with the MIGHTY survey. So I'm going to start by telling you a little bit about MIGHTY, and then I'm going to tell you a bit about a project I'm doing looking at the properties of radio galaxies using MIGHTY. Okay, so MIGHTY is one of the large survey projects currently underway with the Meerkat telescope. I'm sure Meerkat doesn't need much introduction to this audience, but there's a few stats about the telescope on this slide here. Meerkat was inaugurated in 2018 and has been taking some really stunning science images ever since. Okay, so MIGHTY stands for the Meerkat International Gigahertz Tiered Extragalactic Exploration, which is a little bit of a mouthful, and it's primarily a galaxy evolution survey. And once fully complete, it's going to cover 20 square degrees in 4 different fields. The PIs of MIGHTY are Matt Jarvis and Russ Taylor, and you can read more about the survey in this paper on this slide here. So there are 3 main data components to MIGHTY. There are the continuum images, the spectral line cubes, and the polarization data. I currently chair the Continuum Science Working Group along with Catherine Hale. So for the rest of this talk, I'm going to focus on the continuum part of MIGHTY, but I'd like to highlight that the spectral line and polarization parts are also producing some really nice results. So what are the science goals of MIGHTY, or why are we doing this? Well, we'd like to constrain the cosmic history of star formation out to a redshift of 4, and radio observations are a really great way of doing that because they're unbiased by dust. We'd like to understand how black holes are fueled and how accretion onto black holes affects the evolution of galaxies. We want to understand the influence of environment on these processes. How do baryons trace the underlying dark matter distribution? And what can MIGHTY tell us about clusters? So why is MIGHTY the right survey to try and answer these questions? Or as I like to say, Why is MIGHTY mighty? Well, it makes use of the really exquisite imaging capabilities of the Meerkat telescope. But the survey itself has a unique combination of depth and area. It's deep enough that we can detect significant numbers of star-forming galaxies and low-powered AGN, but it covers a large enough area that we can detect the rare, powerful sources, and we can also look at several different environments. And additionally, we're less biased by cosmic variance. But really crucially, if we're going to answer these science questions, the 4 mighty fields that have been chosen are fields with really excellent multi-wavelength data available. And this allows us to get information like redshifts and investigate the host galaxy properties of our radio sources. And that's really important if we're going to understand things like, for example, the interplay between AGN and star formation activity. So mighty observations are currently underway, and the data processing is being led by Ian Hayward. So we've got quite a lot of data in hand already. So far, we've had about 500 hours out of our total allocated around 2,000 hours. We've had observations in all 4 fields, and we've currently got science-ready images in Cosmos and XMM LSS, and early science is underway using these data. Okay, so this is our early science image in the Cosmos field. I hope that the internet connection, wherever you are, is good enough to do this image justice, because I really love this image. As you can see, there are tens of thousands of radio sources visible in this image. Most of them are unresolved, but there are also some really stunning extended structures. And this really highlights the excellent capabilities of the Meerkat telescope. And in particular, its sensitivity to that diffuse low surface brightness emission. So if I zoom in on that image a little bit, so this image was made with 17 hours of Meerkat time on the central pointing, and that covers about 1 square degree. The thermal noise in this image is in the center is 1.8 microjanskis per beam, but due to source confusion, the measured noise is actually around 4 microjanskis per beam. And I'd just like to note that we've produced 2 versions of each image, one optimized for resolution and one optimized for sensitivity. And the one I'm showing you here is the lower resolution image that's optimized for sensitivity. And this is our early science image in XMM LSS, also a stunning image. And this one is made up of 3 pointings, as you can probably see. So I'd like to talk for a little bit about the second of these science goals. How are black holes fueled, and how does accretion onto black holes affect the evolution of galaxies? So I'm going to talk a little bit about radio galaxies. So a radio galaxy is an active galactic nucleus with significant radio emission. And this usually comes in the form of these giant jets, which can be up to many thousands of times the size of the host galaxy itself. So our current understanding is that radio galaxies can be split into 2 different classes based on their accretion mode. So the first class are referred to as high excitation radio galaxies, cold mode sources, or quasar mode, radiative mode, or radiatively efficient sources. These names are all used in the literature, but they all essentially refer to the same thing. And this is this scenario where we've got our supermassive black hole surrounded by an accretion disk and then a dusty torus. And so this black hole is accreting efficiently from cold gas, and then it's radiating efficiently across the electromagnetic spectrum. So if you observed this source in, say, the UV or the infrared, this would look like your typical AGN. And these sources may or may not have a dominant radio jet. The second class of radio galaxy are referred to as low excitation radio galaxies, or hot mode, radio mode, jet mode, radiatively inefficient sources. Again, these names all refer to the same thing. And that's this scenario where you've got your supermassive black hole accreting inefficiently from pockets of cold gas within the hot gas halo. They then radiate inefficiently and they emit the bulk of their energy in mechanical form as this dominant radio jet. And there are some references here that you can read more about this. So for the rest of this talk, I'm going to refer to these 2 different classes as HERGs and LERGs. So why is this important? Well, we believe that radio-loud AGN play a key role in galaxy evolution. AGN feedback is required to quench star formation in massive galaxies, but the mechanisms behind this are not well understood. We believe that Higgs and Lurgs are responsible for these two different feedback pathways. But as I just said, this isn't particularly well understood. So if we're going to understand the role that AGN play in galaxy evolution, it's crucial that we understand these two different accretion modes. So in this scenario that's building up in the literature, we've got radio galaxies accreting in these two different modes. And in this scenario, you should see a dichotomy in accretion rates, with the Higgs all accreting at higher rates than the Lurgs. And this has been observed in several studies. For example, on the left here, I show the Best and Heckman study from 2012, where they used SDSS, FIRST, and MVSS to study the properties of over 10,000 Higgs and Lurgs. And they found a very clear dichotomy in their accretion rates. The Lurgs are all accreting at less than 1% of their Eddington scaled accretion rates, whereas the Higgs are all accreting at higher rates. And in fact, any overlap they do see in the accretion rates of the two classes, they attribute to uncertainties in the scaling relations that are used to estimate those accretion rates. And Beatrice Mingo found something similar in her 2014 study. So we investigated this further using a 100 square degree survey of the Stripe 82 region taken with the JVLA. And we found that this dichotomy was significantly less clear in our study than had been found previously, which suggests that our current understanding maybe isn't telling us the full picture. Note that our survey wasn't directly comparable to these previous studies because we had deeper radio observations. And this might be the reason for this difference that we see, but we didn't have the statistics to be able to say conclusively one way or the other. And this is where MIGHTY comes in, because it will allow us to probe fainter radio powers and hopefully answer this question. So going back to MIGHTY, I've selected a sample of 1,500 radio galaxies from the MIGHTY early science data in the cosmos field. And I've classified these sources as star-forming galaxies in AGN based on these 4 criteria here. And then I've subdivided my AGN into Higgs and Lurgs. I don't have time to go into the details of this, but if you're interested, feel free to ask me afterwards or to contact me. So going back to this question about a dichotomy in accretion rates, what do we see when we then go deeper with MIGHTY? Well, interestingly, we see almost no evidence for a dichotomy at all. There's pretty much a complete overlap in the accretion rates between the Higgs and the Lurgs. And as I mentioned, the key difference is that MIGHTY is deeper. It allows us to probe both fainter radio powers and higher redshifts. And in fact, it's the deep radio data that allows us to reach those faint radio powers, but it's actually the excellent multi-wavelength data that's available in the MIGHTY fields that allows us to reach those higher redshifts. And this is illustrated by this plot here on the left. The black points are the Best and Heckman 2012 sample, where they saw a very complete dichotomy. Then the blue points are our Stripe 82 sample that we used in the 2018 paper. And then the red points are the MIGHTY sample that I'm showing here. So this is suggesting that as we go to these fainter radio powers, it becomes increasingly hard to separate Higgs and Lurgs based on traditional methods. And it probably doesn't make sense to be thinking about this dichotomy in these two separate classes anymore. And actually, we probably should just be thinking about AGN properties as a function of accretion rate, rather than splitting into these two separate classes. Okay, so this is just one project that's currently underway with the MIGHTY Continuum early science data. There are a range of other projects underway, and I've listed some of them here. This list isn't complete. This is just a sample of some of the projects that are underway or starting soon. And in fact, 3 papers have already been published using the MIGHTY Continuum early science data, as you can see here. I just want to highlight one other project led by Jacinta Delhaize at the University of Cape Town. So Jacinta has found 2 giant radio galaxies. So these are particularly large radio galaxies in just 1 square degree in the cosmos fields using the MIGHTY early science data. And this suggests that giant radio galaxies are more common than previously thought. So Jacinta's paper on this was published earlier this year, and there was some really lovely media coverage along with it, which you may well have seen. And this really highlights that it's very early days for the MIGHTY survey, but we're already discovering new things. So watch this space for some hopefully new exciting discoveries. So I just want to leave you with my conclusions. And particularly, I just want to say that if you think that the MIGHTY Continuum data might be useful for your science project, then please feel free to get in touch with me. So I will happily take any questions. Thank you.
All right, thank you very much, Ritam, for the exciting talk about the MIGHTY survey. From the Slack platform, I don't see any question for now, but I believe that people will continue asking questions and engaging you on the platform. Thank you so much. We appreciate it.
Thank you very much.
All right, so I think now we will have our next speaker, and that will be Neo Namane from Rhodes University in South Africa. And she will continue her talk about the MIGHTY, but radio quiet, an investigation of AGN emission. Namane, the platform is yours.
Cool. Thank you very much. Am I audible?
Yes, you are. Yes, you are.
Cool. I'm just checking, are my slides transitioning as they're supposed to? Do you see my slides changing?
Yes, sir, we do.
Yes,
okay,
yes,
cool. Awesome. So my name is Neo Namane, and I'm a PhD student at Rhodes University, currently supervised by Sarah White and Oleg Smirnov as part of the Radio Astronomy Techniques and Technologies group. And before I begin, I'd like to extend my thanks to the AfAS committee for allowing me to present my work at this very important meeting. And I would also like to extend the same thanks to the NRF for providing the funding needed for my research. Now, the work that I'll be talking about today has to do with objects known as radio quiet AGN. And this is done through a multi-wavelength campaign, which encompasses within it the radio observations tied to the MIGHTY survey, which Imogen has beautifully spoken about earlier. Now, my talk is structured as follows. I go into the introduction, wherein I explain the dichotomy that exists between radio loud and radio quiet sources. I then explain the importance of us studying a type of AGN known as quasars in particular. Secondly, I go into the selection of our data, where I detail the selection cuts and the particular telescopes used for the investigation. Thirdly, I go into the preliminary results that I had the pleasure of presenting at last year's SARA conference, bursary conference. And then lastly, I conclude on a few remarks. Now, just to give you an understanding of what radio loudness and radio quietness entail, this is an awesome plot by Padovani and collaborators that portrays the visual band magnitude of a selection of radio sources plotted against radio flux density at 1.4 gigahertz. And what you will notice is these diagonal lines that are representative of the ratio between radio flux density and the visual band magnitude, and the demarcating threshold here, which is shown in the dashed line, is effectively a separation between radio loud and radio quiet quasars, quiet sources, where the radio quiet sources are found below the line, while those that are louder are found above the line. It must, however, be emphasized, though, that the sample used here is not necessarily representative of quasars, because radio quiet quasars form about 90% of the total quasar population. Now, studying the radio loudness or radio quietness of these quasars is exemplified in great work done by Nyland and collaborators, wherein they show quasars that had previously been thought to be radio quiet through the first survey that are now observed to be radio loud as part of the VLAS survey. Now, Asian literature is generally associated with the investigation of the radio emission emanating from these objects. This is shown through the talk done by Zara, where she spoke a bit about dying AGN, where what is called the duty cycle of the AGN can be established, especially in the case of radio loud quasars. And the point associated with my study is also aimed at separating out star formation from accretion activity amongst these candidate AGN. Now, some of you might be asking yourselves what in the universe AGN are. AGN are composed of a few groups of sub-AGN, which are listed on the list on the right, and a pictorial depiction of what a typical quasar, which is a type of AGN, would look like, shown on the left, with the accretion material surrounding the black hole due to the efficient accretion, giving rise to the collimated jets that are observed in the radio. And we choose these particular objects as opposed to safe-fits or blazars, for example, because a comparison to safe-fits shows that quasars are much brighter, and quasars do not necessarily suffer from the Doppler boosting that blazars are often encountered with. Now, the reason why we study quasars in particular also has to do with the nature of the emission. They are powerful producers of electromagnetic radiation, and this allows us to probe high energy physics regimes that are not necessarily probable here on Earth. Another thing that quasars help us to do where AGN are concerned is to help us map out the evolution given their wide redshift range. Now, for our data in particular, as mentioned before, we use a multi-wavelength approach where we use optical, near-infrared, and radio data. For the optical data, we utilize SALT, or the Southern African Large Telescope. This is done so as to attain spectroscopic redshifts of a selection of the quasars of interest within our sample. And this is done through the help of Matt Hilton's pipeline of the University of KwaZulu-Natal. The image on the right is that of the Near Array telescope, which has been spoken about a lot at this conference. And it is essentially a means through which we attain the radio data through what is known as the MIGHTY survey. Now, again, I won't get into the details of the MIGHTY survey, particularly because Imogen gave a wonderful talk on what it effectively entails. But to give a rough background, the MIGHTY survey has principal investigators who are Russ Taylor and Matt Jarvis, and MIGHTY stands for the Meerkat International Gigahertz Tiered Extragalactic Exploration Survey, which is essentially composed of 4 fields. Of these 4 fields, we are particularly interested in the Cosmos field, which spans an area of 2 square degrees. Now, in addition to the optical and the radio data that I've just mentioned, we utilize optical near-infrared data tied to the Hyper-Suprime cam, which is mounted on the Subaru telescope, shown by the image on the left, while the near-infrared data is attained through the Vista telescope, which is done through what is known as the Ultra Deep Vista survey. Now, upon getting all these data products, a collaborator of ours, known as Nathan Adams of the University of Oxford, did what is known as LeFair photometric fittings. Now, for those of you who are not necessarily aware of what typical spectral energy distribution fittings look like, the 2 images there are examples of the SEDs tied to main sequence versus starburst galaxy. And using these photometric fittings, we then constructed what is known as the GJKS color selection plot, which is based on work done by White et al. 2015 and Maddox and collaborators in 2008. And you will see clearly from the gray quasar track that the objects that lie towards the left of this track are clearly misfitted. And we think this misfit is due predominantly to there being stellar sources, while the objects on the right are representative of our active galactic nuclei population sample, where the boxed region at the top shows type 1 quasars that are of interest to us, or quasars that are termed unobscured. Now, you could be asking yourselves why this particular passband selection procedure. Well, this is exemplified by Maddox et al.'s work in 2008, where they have the spectral energy distribution associated with two stellar sources compared to the spectral energy distribution associated with a quasar. And what is characteristic of the two plots is that there's a clear deviation of the spectral energy distributions from the quasar's spectral energy distribution. And this is predominantly why we have a selection criteria that states that K must be greater than 0.9. Now, just to show some of the results that we've been able to produce so far, and again, to those people that attended the CERAL bursary conference last year, I am profusely sorry for showing these again. But the image on the left is that of the AGN radio flux density distribution of our candidates, shown by the orange histogram, while the purple histogram is indicative of those sources with a 5 sigma detection threshold. The blue Gaussian distribution is done so as to account for the really faint radio flux population of our AGN, so that we can have a more complete sample of radioquiet quasars. And the image on the right is a comparison of two independent star formation rate estimates. The first being that which was established by Jan and collaborators, where they use radioluminosity on the y-axis. And the second on the x-axis is one that utilizes optical near-infrared template fittings that I'd spoken about and that were done by Nathan Adams. And you will notice a clear systematic offset towards the radioluminosity that we believe is indicative of there being an additional source of radio emission other than star formation. And in order to ensure the robustness of our solutions or of our results, we then want to employ what is known as the infrared radio correlation, which is effectively an empirical relation that is meant to establish the behavior of star-forming galaxies. This is done through observation of the infrared luminosity established through re-radiation of the dust that surrounds these stars into infrared from UV, and the emission of radiosynchrotron emission through supernovae observed in the radio. And an example of a typical infrared radio correlation is shown on the right, where the authors, Del Vecchio and collaborators, looked at the cosmos field and studied star-forming galaxies within the field. Now, to end this talk off, I would like to state that multi-wavelength astronomy in particular is important in helping us understand the nature of AGN and the nature of the universe's evolution in general. Our results so far show a significant contribution of accretion activity to the total radioluminosity that is observed within these radioquiet quasars. And feel free to write me an email regarding further explanation or potential collaborations. Thank you very much.
Thank you very much, Neo, for the exciting talk and for the exciting piece of work that you're working on. We wish you the very best and congratulations for that. I'm looking at the platform and I can't see any question yet, but I believe that people would wish to continue engaging you on the platform, so keep an eye on that. And thank you so much. So now and to our last speaker for this session will be Claudio Paulo from Universidad Eduardo Mondlane of Mozambique, and he will giving us a talk on statistical analysis of radio halo and relic sample in galaxy clusters. Paulo, the floor is yours.
Hi to everyone, thank you. Let me share my screen. I hope that you all can see it.
Yes, it's visible.
So my name is Claudio. I'm from Mozambique. I'm a lecturer at Universidad Eduardo Mondlane or Eduardo Mondlane University. I will be presenting a work in which originally was designed by Prof. Sergio Colafrancesco. He was my PhD supervisor. And I started this work with him at the University of Witwatersrand in South Africa, but I'm still collaborating with them. For example, I'm under this project now with Dr. Paul Marsegiani, Dr. Charles Takalani, and with my two students here in Mozambique. It's Makukule and Mabots. Basically, this is an ongoing project in which I'm using to keep my life as astronomer back in Mozambique, which is not easy. But anyway, I'm trying to do my best to be online, to be active in the research. So the work is divided in 3 steps. The first one is the analysis, concentrate on the radio relics in which I will present today. The second, we are conducting an analysis of radio halos and relics, taking into consideration the most recent list of cluster with luminosities, entropy, and other data like figures with temperature and density profile. And lastly, we will explore the possibility of Meerkat observation for selected galaxy cluster from our sample. Galaxy cluster represents the large gravitational bound structure in the universe. They can be observed in many frequencies, but in radio, in which is our interest, when we observe them, we see the presence of diffuse emission at the center, called radio halo or radio mini halo, at the peripheral region called the radio relics. Why they are there, we still don't know, and it's still a matter of debate up to date. Here we can see one example of a galaxy cluster, and this at the corner represents emissions from radio relics. At the center, we see here a radio halo. This is a particular cluster in which we see a bridge between radio halos and radio relics. For radio relics in galaxy cluster, in terms of phenomenologies and physics, we see that they are faint megascale extended radio sources, steep spectrum, very low surface brightness. They are elongated or arc-like. They are strongly polarized. They can be divided in 2 main groups where we see double relics, or they can be radiophonics, which are related to radio loud AGN. As I said at the beginning, this is also a manifestation of diffuse emission in a cluster. Why they are there, we don't know, but there are some possibilities. For example, for the case of radio relics, they can be related to DSA theory or not. Even we are not clear about the link between radio relics and radio halos, other galaxy cluster parameter and the radio galaxy. But there are common explanations for the origin of radio relics, which can be emission from shocks, reacceleration of electron. But this mechanism shows some or several inconsistencies. For example, observations show that the position of relic doesn't coincide with the position of X-ray shocks in several cases. The Mach number at the outer edge of the relic derived from the temperature difference is significantly lower than the value derived from the radio spectral index, assuming a DSA theory. So if DSA model is correct, we expected to see something from gamma ray emission, which is not happening. If in terms of geometry, we usually ask, why relics only in the periphery of cluster and not in the center? Sometimes we see galaxy cluster with bridge between radio halo and radio relics, and we don't know why this is happening. For that, or to give our contribution to this field, we decided to find an alternative explanation. So we decided to compose a list of galaxy cluster available in the literature, and we managed to get 6 galaxy cluster with radio relic detected. Inside the 6 galaxy cluster, we had a sample of 77 relics, in which 43 are single and 17 are double. And in our alternative explanation, we have tried to start the correlation between radio relics power with radio halos power and other galaxy cluster parameter like SSSZE effect, which someone spoke about it in few time ago, X-ray bolometric luminosity, and cluster cooling time. We also explored the correlation between radio relics and Mach number and radio relics with active galaxy cluster, with active galaxy in the cluster. When we use, or when we see our results, we can see, for example, from the image on the left, the link between the power of relics and halo. We can see that relics knows about halos because they scale together. When explore the correlation between cooling time and radio relics, we can see here that there is a possibility of connection between them. When we explore the link between YSZ and relics, bolometric luminosity and relics, even with low statistics, we see that there is a trend between them. So there's no very good correlation. So this means that we need to increase the statistic, but we can see that radio relics are linked with the properties of liquid properties of cluster. There's a correspondence between the thermal and non-thermal electron population in the ICM, or between the galaxy distribution and the non-thermal electron population. Our first paper in this project link us preliminarily with the correlation between Mach number and radio power, because we know that the main problem about the origin of radio relics is the understanding the source of relativistic electron that produce radio emission. In the common assumed approach, this is connected to the presence, this is connected to the presence of intracluster shocks that are supposed to accelerate particle to high energy through DSA. Such a scenario requires strong shocks with Mach number greater than 5. From the theory, we see that in the strong limits where Mach number is greater than 5, the correlation between the Mach number and the power of radio relics show a pattern or can be expected to be constant. When the Mach number is smaller to 3, the radio power is expected to be strongly decreasing. But when we use data from INSON 2004, we see that there is no change in the slope between the power of the radio relics and Mach number. For Mach number smaller than 3, the observed slope is smaller than the theoretical one, whereas for Mach number greater than 3, the expected flattening of the relation is not observed. So a lack of change of the slope can instead indicate adiabatic compression as alternative scenario, as we can see. So this evidence indicates that the general shock acceleration theory is not consistent with the observed, radio relic power distribution, and therefore it cannot be considered as a representative model for the origin of radio relics in the cluster. This argument seems to strongly contain the DSA scenario for the origin of relativistic electron population necessary to produce emission. That's why we decided to go in deep and produce our second paper, in which we can see here, which is the correlation again between Mach number and radio power with a different approach. We decided to find the correlation between the Mach number derived from X-ray and the Mach number derived from the peak values of the radio spectral index, as well as with Mach number derived from the values, from the average values of radio spectral index, where we can see here how they behave. So we can see that there is a lack of correlation between relics and power and shocks. And the question is, why relics power are correlated with the property of galaxy clusters, but not with Mach number? There should be two factors that contribute to form a relic. One is related to the cluster as a whole, and the second not directly related to the shock strength. This second factor can be the presence of radio galaxy, jets, and or lobe in the shock region. So that's why we decided to come to, or to go to a new approach motivated by the shock relic connection. On the left, we know now, or until now, that shock acceleration from the thermal pool bring us Mach number problem, make the DSA theory confused because there is no gamma ray detection. We only see upper limit, for example, from the Fermi-LATs. Shock acceleration of a relativistic shock electron maybe can be past radio galaxies activities in the galaxy cluster. So that's why we decided to pick some well-known galaxy cluster to see what is the link between the radio relics appearance and the galaxy and radio galaxies close to them. We explored this. We identified L, M, K, and X radio sources, where we find that L, possible dark matter halo, M, it's not clear if it's physical connected to the cluster, and X and K, which are very close, we decided to analyze their SED for the source K. We can see that it's completely dominated by non-thermal emission, but without any evidence of association to the host galaxy. We explored source X. We find very close to the source, two source spatial correlated with them. The SED show non-thermal emission. From the map of the spectral energy distribution of the source X, we see a pattern which is similar to the pattern of the relic. Maybe the source X is emitting the electron with the presence of something being reaccelerated and creating the presence of the radio relics. So in terms of summary, we can see that relics are associated mainly to various forms of galaxy non-thermal activity, maybe compression of magnetic field by the shocks, arc-like maybe are linked with AGN jets, double maybe are linked with radio galaxy lobes, intermediate maybe are connected to galaxy feedback radio mode. For that, we need a systematic study of relics over a large homogeneous sample. Maybe the MIT will increase the population of galaxy cluster with diffuse emission, maybe SKA survey. There's a preliminary study from CAT7, from NEBA, from WITS. He is still working on it. So this is what we are going to do next, to build our sample with increased number of galaxy cluster with observation from many or different wavelengths. And currently, I'm working together with Dr. Charles and Dr. Paolo Macegiani with 2 students. We are conducting an analysis now of radio halos and relics, taking in consideration the most recent list of clusters with luminosities, entropies, and other data. This is a work in which is being supported with a very limited funds from Doppler and Dara. So this is one student in our lab here at this is Makukule, and this one is Mabot. Thank you.
Thank you very much, Paul, for the exciting and detailed analysis of radio relics. We appreciate the contribution that you've given to this session. And allow me to take the opportunity to thank all the participants, those who given the talk in this session, and all those who found time to attend the session. I think that was the last speaker, so we will be breaking for the lunch. And because I don't see any question for any of the presenters, and I also don't see any request for an announcement, so I'll take the chance to thank you all and to wish you a good lunch break. And I hope that you'll find time to attend the afternoon session. So the afternoon session will start at 12:30 Central African time. Enjoy your lunch, everyone. Thank you.